Let me begin with a word of prayer. Heavenly Father, we thank you for this day again. I thank you for this class and these students. Just ask you to be glorified at what we do, Lord. In your name I pray, Lord Jesus. Amen. So I just gave you guys back your quiz 6, and there you go. So let me just talk about that for a second here. Also, I have a handout for you guys today. So this is from the required textbook with the, is it Chartan? I can't remember how the author's name goes. Chartan? Okay. Anybody happen to remember the names of the authors of this book? I meant to write it on here. So I'm going to post this again. In fact, I'm probably going to post the whole chapter 6 as a PDF and course content for you guys, just in case you don't happen to have the book. I mean, I bought the book, and then my children lost it, and I'm not buying another one because it cost me $100. And this book is, the required book is kind of a pain to find, and I have mixed feeling about it because it is kind of nice in the sense that it's lengthy, right? So there's 600 pages in the required book, as stacked up against my, 150 pages of notes at the moment. So in some sense, the book is more helpful because it has more, right? And then, of course, when I make mistakes, then the value of the book goes way up, right? But as long as there aren't similar mistakes in the book. Now, an issue was brought to me after class last time, and I have to study the way I have things written in the notes more carefully to decide if I need to edit the notes and how I need to edit the notes. But I think I have said that induction constitutes showing the implication Pn implies Pn plus 1, right? This is not true. It's a little bit different than that, because what we're actually having to do is we're assuming Pn is true, and then we're showing that that implies n plus 1, right, is true. So it's not really an implication in the wild sense of like, if P of n is false, then the implication is automatically true. That does not count, because it's not just an implication without any kind of comment about the antecedent, right? We're assuming the antecedent of the implication is true when we do proof by mathematical induction. And that's still true in the case of strong induction, right? So I think last time I said you have to show P of 1 implies P of 2. And I think that's actually true as I talk about it now, because when we write P of 1, that is, the meaning of that is P of 1 is true. That's our custom. So, but I can totally understand that you might think otherwise. Like, that's a reasonable misunderstanding of what I was saying, because like one of you came up to me after class last time and was like, wouldn't this like automatically be true? Because if the if all the antecedents are false, then we have attained all of the implications vacuously. So any statement you can write about a proposition in terms of a natural number is automatically true for all n, right? I mean, something's wrong about that, obviously. So there's something missing in my statement of how we do induction proofs. Now, if you look at the proofs we did, I always did what? At the start of the proof, I assumed, in the middle of the proof, I assumed that the induction step was true, and then I used that to show that n plus 1 is true, right? So the sin, if you will, of mine, if anything, is not emphasizing that we're assuming the induction hypothesis is true. And in strong induction, we assume not just the induction hypothesis is true, but not for just for an arbitrary n, but rather for what? For all of the integers in the inductive set, starting at the base point, wherever it is. So this handout I just gave you guys, everybody have one? Okay. The first page is the statement of mathematical induction, principle of mathematical induction in chapter 6 of the textbook. Again, I think it's, I forgot the names of the authors, my bad, but I'll put it in the video description. So this is on page 154, principle of mathematical induction. How's it go? For each positive integer n, let P of n be a statement if P of 1 is true. Then if number 1, P of 1 is true, right? And number 2, for all k in n, P of k implies P of k plus 1 is true. Then for all n in n, P of n is true, right? So on the surface level, it might look like we're proving an implication, right? But it's not quite that. We're presupposing the truth in like step 2, we're presupposing that P of k is true, and then we're showing that pk plus 1 is true. Like that's what that notation means. Pk means that the proposition P of k is true for k. That's the shorthand being used here, which I think there is danger for confusion there. And all right, so then if we look at the, so I just gave you guys back your quiz, and most of you did very well. I think about half of you are like exactly where you need to be, and about half of you still have some things you're working out. So like, if you got like a 7 out of 10, what that means is there's some kind of like somewhat serious error. I'm pretty, if you got a 5, there's like something serious missing. Like there's the big idea, which was to, bridge the gap between 1 plus 2 plus da 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 plus n and n times n plus 1, right? Like a proof, an inductive proof on this proposition, right? Oh, my bad. 1 plus 2, this thing, right? So the people I gave a 5 to on this quiz, all they did was just work with this. They did nothing with this over here, right? You've not meaningfully engaged the problem if you've done that. You've deceived yourself into thinking you've done that, but you didn't, all right? Maybe you've showed that, well, I don't know what you showed, but it's not this, all right? All right, so here's the other, I wanted to just comment on the main mistakes I saw because we'd like to, most of these mistakes are easy not to repeat. So if this statement, right, is Pn, right? If we say, so that's an equation, right? And that's true. That being true means that when we plug in n, we get equality here, right? So some of you have written this. In fact, a lot of you have written this. And I don't think that's a reasonable thing to write. I don't think we should say that Pn is equal to the equation. I mean, Pn is, see, this is where it gets tricky. Pn is the equation, so perhaps Pn is equal to the equation, but I shouldn't put equality here, right? These are not equal. This is true, right? Or false, perhaps, if you extended the meaning of n past the natural numbers, right? Say, for instance, just for a second here, that n could be a real number, right? This would not be true unless n happened to be a natural number. So this proposition then could not be true or false, right? As it stands as a tautology, as long as n is a natural number. So this is either true or false. This is a number. True or false is not equal to a number. We cannot write equals here. All right? This is fuzzy thinking. So I've tried to take off a point if you did that. I think one of you only took a half a point off because, like, otherwise it was better than some other people's solutions. But all right, so that's the one thing. The other thing is, if you look at the book the handout I just gave you, right? I don't know if you can see it or not. Maybe on the next page I didn't share with you guys. When I post when I post the PDF later today, all right? If you look at the next page I haven't given you, I think. If you look at page like 155, which you can't look at because I didn't give it to you, all right? So you can look, but you're not going to find it unless you've got some kind of like special ability. But I don't. You're cessationists, many of you, so you wouldn't believe in the gifts, and so as such, as be a self-fulfilling prophecy that you wouldn't be able to see the next page. But sorry, as far as I know, seeing the next page in a math textbook is not a signed gift that any even charismatic church believes in. But sorry, somewhat of obscure comment there. But on page 155, when you can look at it, what you'll see that they do is they take this, and then their next step is to go, okay, so then add n plus 1 to both sides. So I said use words. This is more what I'm talking about, okay? Like this. Instructions are hard to be sometimes it's hard to give instructions which really clearly communicates what I want from you guys. So when I say use words and sentences, I don't mean everything has to be words and sentences. Some of you took it to be that and still survived. You gave a good paragraph. That's hard. That's actually very good. I personally am much more typically successful if I use a column stack format for this kind of problem. So this is the left-hand side of the Pn plus 1 claim, right? But you notice what I've done here. I've started with the induction hypothesis. If you can put yourself at that part of the proof, I've started with the induction hypothesis, which is assumed to be true, right? Then I add n plus 1 to both sides. This is an allowed algebra step, all right? So, and then what I'm going to do is algebra. So I'm going to be like, okay, well, so this is by the induction hypothesis. And then if I factor a half out, you know, let's see here, 2 times n plus 1, right? And then that is 1/2 n plus 1 times n plus 2, which is 1/2 n plus 1 times n plus 1 plus 1, right? So therefore, p of n plus 1, true. So what I've done is I've started with something that's known, that we're supposed to assume in the proof, at the start of the proof. Then I do algebra steps, and I then show that the alleged proposition is true. Those of you who I took points off of, largely speaking, what you've done is you've written p of n plus 1 at the top of the proof. And then you've done steps, basically, to get down to something that's of the form 1 equals to 1, or n plus 1 equals to n plus 1. That is not a valid proof technique in here, all right? You have to reverse those steps. Like, in principle, you could take what you wrote and start with n plus 1 equals n plus 1, and then go to the next step, and go to the next step, and go to the next step, until you finally got to p of n plus 1 as a statement, right? That would be valid, because proofs are read top down. But when you write the thing you're trying to prove at the start of the proof, you're assuming the point. At least you're giving the reader the sense that you're assuming the point. Like, I have to do a lot of work with your proof to make sense of it, because I have to read the whole thing, and I have to go to the very end, and I have to retroactively read it back up. I shouldn't need to do that. That's why I took points off, okay? So I want you to see that on a low-stakes quiz rather than test 2, right? So hopefully what I'm saying makes sense. Now, ultimately, look at my solution like I'm giving you only a partial story here. The full solution is going to be posted, obviously. And anyway, I think a lot of you guys are a lot of the way to where you need to be in terms of induction, so that's great. Any questions before I say more? Yeah.
So for induction in general, do we start, when we're doing like the second part of P of n implying P of n plus 1, do we start with P of n and then do things to it to get P of n plus 1? Or can we ever start with P of n plus 1 and do things using the induction hypothesis?
We should not start with P of n plus 1, except so you'd be like, well, you're being hypocritical because in your proof of the binomial theorem, you kind of started with P of n plus 1. That's a little bit true, but a little bit not. See, because if you look at the proof I gave of the binomial theorem, what I did was I wrote the binomial theorem for n, and then I multiplied that by a plus b, which got me to the left-hand side of a to the b to the n plus 1, right? That gave me a formula for the right-hand side, which was non-obvious. And then I did some algebra steps. I got to some point. Then I went back to, and in all of that, I never used the induction hypothesis. Then I went back to a to the b plus a plus b to the n plus 1. I did an algebra step. I used the induction hypothesis. I rewrote the sums after making a substitution. And then at some point I got to like where 4.2 and 4.3 match. So I met in the middle. So I'm not saying it's universally the case that you have to start with the left-hand side of what you're trying to prove and get to the right-hand side. It's just when you can, that makes for the most clear proof. Like, it's not always possible. Sometimes we have to meet in the middle. But if we're going to write down the n plus 1 proposition, we should be very clear with language saying something along the lines of, this is what I want to show. I have not shown it yet. This is our goal to show this. And then you don't put equality onto that. You write that down so you know what you're looking for. Then you go back and you start working on like the left-hand side or the right-hand side of the equation, if it's an equation we're talking about. Of course, there are other things in equations, right? There's like divisibility statements and all kinds of other things. But so the handout I just gave you I'm excited about, maybe excited is too strong a term, but I'm excited. So this actually has some more examples of strong induction, which are sadly lacking from my current set of notes, right? So you guys, let's try to work one of these before I go on here. What would you guys like to work? Student's choice. We can work example 620, or we could try, maybe we could try result 6. Let's try result 6.22. That one seems kind of interesting. The examples, the two examples before that are examples of so-called recurrence relations. I guess maybe, let's try to do 2. If it doesn't take me too long, we'll do 2 today, okay? So this is result 6.22. And my apologies if I'm accidentally doing your homework. All right, so for each integer n greater than or equal to 8, there are non-negative. I really want to put a dash in that. I don't know. Non-negative integers a and b such that n is equal to 3a plus 5b. Now, allegedly, this claim is something we need to use strong induction for. Let's see if we can understand how let's just work through the argument right as it's written. I'm not going to try to reinvent the wheel or anything here. We're just going to write down what it says in the book and try to understand it together, all right? So here we go. So you proceed by, oh, I'm sorry, this marker's hideous. Induction. Yeah, well, that's kind of obvious. Proceed by induction. Well, thanks. That's helpful. But yeah, that's, yeah. I'll eventually find a marker. All right, notice this marker is also dying. 8 is equal to 3 times 1 plus 5 times 1, right? Thus, goodness gracious, let us, for the sake of not writing that again ever, call this sentence what? We will call this P of n, right? That's the other thing I complained about on some of your quizzes, is you never told me what P of n was. You just assumed I knew. I don't know, right? Maybe it's a tautology, like all cats are evil or something. I don't know. But so thus, P of what is true? P of 8, true, right? What's next? All right. So we're going to assume for each integer I with 8. Let's see here. Let me write it out. Assume for each I in Z with 8 less than or equal to I. Would it have mattered if I had said K, said natural numbers instead of Z here? I don't think so, right? For each I in Z, or you could write N there if you wanted, with 8 less than or equal to I, less than or equal to K, there exists non-negative integers S and T such that I is equal to 3s plus 5t. So what could you put that everything I just wrote in black just a second ago here? What's another way we could say that more compactly? Like, how could you summarize what I just wrote? In other words, we're saying what? We're saying that P of I true what? Well, P of I is true, right? That's what that is. So we're supposing, if you think about this, we're assuming that P of 8 is true, P of 9 is true, P of 10 is true, all the way up to P of K being true, whatever K is, right? Now, so this is strong induction because we're making the assumption that the induction hypothesis holds for every case from the base case all the way up to the induction step. So then we consider K plus 1, right? And then what do we do here? We show that there are non-integers. I'll write down. It says we show there exist non-negative integers this time he's using x and y. Such that k plus 1 is equal to 3x plus 5y, right? All right. So this is something I haven't done too much in here. Sometimes in a proof we write a sentence that says what we're about to do. All right? So this is telling the reader, I have to keep reading to finish the thought, right? Have I done that yet? Well, no, right? This catches me off guard when I'm reading books, right? As you read higher level math books, this is a common practice, is to write a sentence describing what you're about to do. And if you don't recognize it as such, it's very confusing because you'll be looking for the question like, wait, how was that shown? And the answer is, it hasn't been shown yet. This is what you're going to show, right? So this we show is important, all right? If that's not there, I would take points off. But like sometimes it happens in books, as you're reading, sometimes it's really important to read the next paragraph in order to make sense of that sentence. I have wasted many an hour on this problem. Okay, anyway. Okay, so then what do we do? He says 9. Notice 9 is equal to 3 times 3 plus 5 times 0, right? Where 3 and 0 are non-negative, right? And also 10, how can we get 10 as a sum of 3 and 5 with non-negative coefficients? Very good, 3 times 0 plus 5 times 2. So thus, basically we have P of what? P of 9 and P of 10 are true, right? And we see x equals to what? Like x equals to 3, y equals to 0 for k plus 1 equals to 9, or x equals to, what you just told me, 0, y equals to 2 for k plus 1 equals to 10. All right. Maybe that's not entirely necessary, this last sentence, but just to be to be abundantly clear, that's what happened, right? I was robbed. Should have gone here. Oh well, I'll get over it. So anyway, moving on. So what next? Hence, assume that k is what? Greater than or equal to 11. Why is that reasonable? If I was to put a parenthetical comment to explain that further, what would you put in the parentheses? I would put, because we've already shown k equals 8, 9, 10 are true, right? So it just remains we can focus our attention on k being larger than or equal to 11, all right? Because we've already addressed the other cases. Okay, so then, thus, 8 is less than or equal to k plus 1 minus 3 which is less than k. Where's that coming from? I mean, this is k minus 2 altogether, right? So it's quite clear that k is larger than k minus 2. That's not profound. This, on the other hand, is coming from what? This is coming from that k is, if k is greater than 11, then k plus 1 is greater than or equal to 12, right? So this follows from the k greater than or equal to 11 statement there. So then by the induction hypothesis, what? There exist A and B in Z with AB greater than or equal to 0, such that what? Man, all my markers are trash today. I was robbed again. I was robbed. That was a legitimate throw. I should have gone in. Actually, what am I saying? It went in. There's no photographic evidence to the contrary. Let's see here. I should have like a cut screen I edit in that just shows a marker like swishing into the trash can whenever that happens, you know? If I actually edited. Okay, so then what? We got, I've lost my place here. By the induction hypothesis, we get k plus 1 equal, k plus 1, good grief, parentheses, minus 3 is equal to 3a plus 5b, and that implies what? So does that make sense? Why can I do this? K plus 1 minus 3, see this? K plus 1 minus 3 is less than k, so the induction hypothesis applies to this number, which means I can write it as a sum of 3 times a plus 5 times b for some non-negative a and b, all right? And then once you have that, you can solve that for k plus 1 is equal to what? Well, 3 times a plus 1, right? Plus 5b, where clearly a plus 1 and 5b are non-negative, right? So, you know, identify x equals to a plus 1 and y equals to b, and this completes our argument to show p of k plus 1 true. Now, do I need to write all of this? No, probably not. This is probably a little bit much, but I'm just trying to be a little bit more verbose on this proof for a second here. Do you see why all right, so like this one, it was necessary to add this additional assumption of k being larger than or equal to 11 in order to gain access to this inequality here, right? So that took insight, right? That's not an obvious step. But if you think about it, you're trying to show, this multiple of 3. So if you think about it, if I can somehow get back 3, then that gives us a 3 over here. But of course, then all of this is equal to the integer linear combination 3a plus 5b, which means then we can use that minus 3 to lump it back into the other side, and that gives us what we want. Yeah.
Why does k have to be equal to like 10? Why do you have to show both these right?
Well, we've already shown 10, so we need to show proof for 11 or larger. So we're trying to show that the inductive set includes every number larger than 8. So if we've taken care of 8, 9, and 10, then we have to start giving evidence at 11. I don't think we could, though, because if we only had 9, like getting having 10 is what we needed for this this inequality to hold for k plus 1. I mean, I know this argument works. You're asking, could a slightly less, like, could we go one back from what's been done here and still get it? I don't know. Maybe. I don't. Probably not, because it's in the book. But anyway, so that's an example of strong induction. I think there's one in your homework that's kind of like this. I have an example like this linked in the notes. Right? There's another example similar to this. I don't think it's this exact example, hopefully, but yeah. So any questions here? Yeah.
There's one thing. I think, at least on here, when you have
Uh-oh.
k is greater than or equal to 11, it's k plus 1 is greater than or equal to 11.
Oh, is that what it is?
That might be, yeah.
I think then if I do that, then you're probably happy, Sammy, right? Is that it? Yeah. Because that's the same as saying k is greater than or equal to 10, which is what you were lobbying for here 5 minutes ago. Wait a minute, 2 minutes ago. Time flies when you're having fun. All right, so I think I've taken too long for this example to do 2, so you'll forgive me, but there are another like 5 strong induction examples to appreciate. Like 3 of those are all recurrence relation examples. So I will try to post a video working through one of those examples. I'm making work for myself, but I'll try to do that for you guys. But I think we should go on to the next topic at this point, which is, I think, something entirely different, actually. And that is the topic of relations. So what is a relation? This is the next story arc in this course. So chapter 5 in my notes. What is a relation? So in short, a relation from A to B. So we have 2 sets, A and B, all right? And a relation from A to B is simply a subset of the Cartesian product of A and B. That's it. So, I mean, what are examples of relations? Well, give me a subset of A and B, A cross B, and that defines a relation. Now, that's pretty open-ended, right? So as we go on here, we'll talk about certain kinds of relations that have a special structure, like we could talk about order relations or partial order relations. If we have a subset of a set Cartesian product with itself, that's called a relation on A itself. Perhaps in my opinion, the most important kind of relation is called an equivalence relation. We'll spend a good amount of time studying those, all right? But let me just give us the basic definition here. And then hopefully we'll look at a bunch of examples. So, definition, let A and B be sets. We say R is a relation from A to B. If R, and yeah, is this often the time the case in definitions? This could be an if and only if, because I don't know. We're sloppy about this in mathematics. We a lot of times write if in a definition when we really mean if and only if, truth be told. Because what I'm about to write defines relation, all right? If and only if R is a subset of A cross B. All right. Moreover, so now I'm going to tell you some notation. We write X, R, Y, if and only if, I'm changing all my ifs to if and only ifs. Sorry, guys. I feel obligated to do it in here. If and only if X, Y is an element of the relation, all right? If X is related to Y, then we say X is related to Y. If you look at what I wrote, I said some. I said I didn't. It seems like I didn't say anything, but I'm writing something. If X is related to Y, then we say X is related to Y. You see what I'm saying? So this notation is read like that. All right, and sometimes you'll actually not just say that, but if you have more than one relation involved, you might say it like this. X is R related to Y. This also language is the language that you can use if you want to emphasize it's the R relation. Maybe there's more than one relation floating around, okay? On the other hand, if XY, the pair XY is not an element of the relation, then X is not related to Y. So we also use that language. When we say, that was supposed to be a when we say X related to Y, we say X is the input of the relation, and Y is the output of the relation. All right. Does this seem familiar? Have you seen anything like this before? Inputs, outputs? It should be somewhat familiar to you, right? We talked about functions, right? This is somewhat reminiscent of a function, but there's something important missing here. So here we go. We will eventually define function as a special kind of relation, okay? That's the other very important kind of relation, is a function. So the domain of R is X in A, such that there exists Y in B, such that X is related to Y. The range of R is Y in B, such that there exists X in A, such that X is related to Y. Finally, yowzers, this is enough. This is quite a definition, isn't it? Finally, if R is a subset of A cross A, then and that's important, and the domain of R is equal to A, all right, then we say R is a relation on A. Whew. All right. Yowzers. So let me just, yeah,
What's that wording from the parentheses R equals A?
this one or,
On the bottom, so like finally if da 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 and what?
oh, domain. Yeah, I'm sorry. I seem to have no sense of capitalization consistency. So apparently I also have this as a notation for domain, depending on when I type things. I mean, I've got capital domain here, and then it become lowercase dom down here. But yeah, my bad. Sorry. I think there's about like 5 quiz questions in here, right? Like, you know, like I wouldn't make this all one. I don't want to grade all this. I would like break it into pieces, right? Like, what does it mean for R to be a relation on A? Versus what's the, you know, if R is a relation from A to B, define the domain of R, define the range of R, right? Those are decent like next quiz questions, for example. Let me, before I get any further, contrast this to function notation, which you might have already seen, right? So I'm putting the cart before the horse here, and like it's just inevitable because you guys already know what a function is, right? How many of you have taken like Dr. Sprano's like calculus class? Calculus 1 with Sprano? Anybody? No? Does that not exist anymore? Maybe not. But anyway, first test, first question, always define function, right? So a function is, so like if I write f as a function from A to B like that, this presupposes, among other things, that the domain of f is equal to A, right? So that's one significant difference between the function notation and the relation notation at the moment, is that we do not suppose that a relation on A is necessarily defined for every element of A. Right? That's kind of a big difference. The other more significant difference is that a function has to be single valued. All right, but a domain, a relation does not have to be single valued. There could be one input which produces multiple outputs. That can't happen with a function. All right. But anyway, talk more about functions later. Let's focus on relations for today. So, I mean, what's an example of a relation? Like, well, what's not an example of a relation? I don't know. I mean, there's so many examples. Let me give you some. So example 1, oh, people. Let S be a set of all living creatures on Earth. We say X related to Y, if and only if X and Y are both people. All right? So in this sense, I am R related to Trump. All right? On the other hand, I am not R related to Napoleon because he's dead, right? I'm also not R related to Gene Hackman, also dead. That one's ripped from the headlines. If you didn't know. You guys don't even know who Gene Hackman is, so like, what am I? The villain from Superman that you haven't watched. Let's see here. I'm also not R related to my mom's dogs because they're all dead. But if they were alive, I still wouldn't be related to them because they're dogs, right? This is a very silly relation, but you can think about relations like this, right? Like if you read the text, most textbooks have like a couple examples on like parent-child relations, that kind of thing, right? Like related to. Like relations. Okay, you can make those. All right, enough of this. A slightly less, but only slightly less silly example. I call this circle, the circle relation. And here it is, R equals to XY in R2. What is R2, guys? That's a shorthand for what?
Two-dimensional space?
Right, but it is, in terms of the Cartesian product, it's what? It's R cross, but you're right, it's two-dimensional space, two-dimensional Euclidean space, we might say. That's, you know, R2 is R cross R, right? okay, so question, is this a relation on R? What's the domain of this relation? What's the range of this relation? I think they happen to be equal, right? Because I can graph this relation. Conversely, by the way, if you pick any graph, right, that is a collection of all points, x comma y, that satisfies some equation perhaps, right? It gives you some shape in the plane. That defines a relation because it's a subset of the plane, right? Now, does that define a relation on R? Probably not, unless your graph does what? Covers all possible x values, right? Does this one? Certainly not, right? The domain here, if we study the circle, -1 to 1, in fact, that is the range as well. Because all possible inputs are -1 to 1, all possible outputs are also -1 to 1. So this is not a relation on R. Although it is a relation on R cross R. All right, I'm emphasizing that a little bit because it snuck up on me. I think I forget this sometimes when I step away from this material. Okay, so the next example, I have also called circle in the notes, but that's not accurate. I'm missing an S. Circles. All right, so here the relation is, and I probably should change the letter. I think I'm using R in the relation to define the relation. Not a best practice, really. X, Y in R2 such that there exists, let's say, A in R such that x squared plus y squared equals to a squared. This is, in fact, a relation. What does this look like? Can we graph these? Like, can we picture these? What are we talking about? How about this? The origin is what?
=0.
Very good. You pick any other point. Is it covered? Is there some circle that goes through any other point in the plane? Search your heart.
Yes.
Find it to be true. Yes, very good. So we could say that circles, divide up the plane. So like, we could be here all day, right? Like this is not all of them, So in this case, in fact, the domain is everything. The range is also everything, and this is a relation on R. It turns out this is an equivalence relation. The reason I know that without further study is it does what's called partition the plane. It divides the plane up into disjoint sets, which are non-overlapping. Every circle goes through a point, and there's only one circle that goes through that point. If we're talking about circles concentric from the origin, there's a unique circle through each point. And then there's the origin. That's a partition. Okay, so another example. Disk. We could do something like R is x comma y such that in R2 such that x squared plus y squared less than or equal to 1, right? The graph of this is this, solid disk, right? So here, it's kind of funny. This has the same range and domain, right, as my example 1, yeah? Got the same range and domain, but it is certainly not the same relation, right? Here, we have, for example, 0.5 is related to, you know, minus 0.2 or whatever, right? That's a particular point, like here-ish, right? It's an element of this relation, right? In contrast, in my example 1, 0.5 is not related to minus 0.2, right? Because 0.5 squared plus minus 0.2 squared is not equal to 1. So in terms of my example 1 relation, these would not be related. So I can go all day with these examples. I love them, but you know, let me try to draw it to a close here. xy in R2 such that x squared plus y squared greater than 1. If I was to graph this, I'm talking about what? Outside the unit circle, right? So it's like everything out here is in the relation. What's the domain and the range of this relation? Is this a relation on R? I think it is a relation on R because I think the domain is everything. Every x is attained, right? There is it's not inside here, right? But there is x, every x is reached by some point in the relation. There's an input for every possible real number is an input for some point, and every possible y value is an output for some point, right? What's missing here is gained up here or over there. All right. And then finally, we could also do things like a lattice. Something like R is equal to natural numbers cross natural numbers as a subset of R cross R. So this is another kind of relation that's, I mean, so you guys see that some of these are, you could attain with like, you know, an equation or something. Some of them we've attained with inequalities. Some of them are just really, I guess, set theoretic in nature in terms of their definition. Here's a picture of this relation. It's just the integer, the positive integer grid, 1, 1, 1, 2, you know, 2, 1, 2, 2, 2, 3, 2, 4, and so forth and so on. I mean, it goes on, right? This is a relation from R to R. Again, what's the domain?
Natural numbers.
Yep. What's the range?
Natural numbers.
Very good. We could do the same example, replace n with z, right? We could do z cross z. That would give us the integer lattice. That's another relation from R to R. All right. Enough about that. So we can also talk about, let's see here. I do have my example 7 here. Well, it's actually my example 10, but I'm going to call it's example 7 today. So here's one. Well, this is the other one. Q cross Q, basically. I'll just get to it. Q cross Q is a subset of R2. This defines a relation R. This says that X is related to Y, right? If and only if what? X and Y are both what? What does it mean for a pair to be in the Cartesian product? It means that the first component's in the first product and the second component's in the second thing product. Here that means that both X and Y are rational numbers, right? This one is hard to graph, right? What's the grid of rational numbers? Yeah, it's everything, right? Here, let me draw you the rational line. There you go. There's Q. It looks the same as R, doesn't it? Because there's infinitely many rational numbers, and they're infinitely close to one another. All right? One of the great weirdities of mathematics is that there are many, many, many more irrational numbers, all right? There's actually many more irrational numbers. It turns out that there's like the same number of rational numbers as there is integers. We'll study that towards the end of the course. In contrast, there are as many irrational numbers as there are real numbers. And I will give a precise meaning to these vague comments much later. But yeah, the graph of Q is kind of hard to appreciate, right? Because if you take any two rational numbers, right? If this is P and this is Q, if you take the one in between, right? P plus Q over 2, that's still rational, right? Because the sum of the average of two rational numbers is still rational, right? So between any two rational numbers, there's another one. And you can do this with many other fractions except for this, right? There's infinitely many rational numbers between two given rational numbers. Yeah. So I don't try to graph that. All right, so let's talk about other things we can do with relations. What else? What do we do with functions? Well, I guess we did things like add them, right? We subtracted them, we multiplied them. And I don't think we're going to do any of those things with relations because a relation is just a subset of the Cartesian product of two sets, right? So like, why would I even be able to add their values or multiply their values by a number, you know? But one thing I can do with relations is I can possibly compose them. We can look at a composite of two relations. So let me try to define that for you. So here it is, definition. Let R be relation from A to B, all right? And S a relation from B to C, then the composite of R and S is S composed with R equal to, parentheses, A comma C, such that B is in B, I'm missing a there exists there probably. There exists B in B, all right, such that A, B, oh man, let me try this again. There exists B and B, I'm trying to think of how to write this. So I'm just going to write it as in my notes, and if it makes sense to us, then great. If not, well, my apologies. B and B such that AB is an element of R, and there exists C in where C such that BC is an element of S. I probably owe you there exists right there. There exists B and B such that AB is an element of R, and there exists C and C such that B comma C is an element of S. That's what it means for AC to be in the composite relation here. All right. So let me give you guys an explicit example of this. Example 8, I guess. All right. So here I let R equal to specifically the following set of 4 points. 1, 2, 3, 4, 5, 6, 7, 8. Those are pairs. All right, and I let S be the